Hi everyone, thanks for your presence. Let's talk about a project at the UI that we choose after we run several innovation sessions. Those innovation sessions was conducted using design thinking, double diamond to discover a new kind of product and as well to rethink the way we do business. UI is a accounting firm just like others, and we need to check and validate new model business, just like recurrence or subscription models. So here I present to you the Aleph. The Aleph, it's a product based on subscription, and the Aleph addresses the main challenges in Brazil regarding to the litigation. So in Brazil, we'll have almost, if you count how much the companies expense in litigation, in labor, tax, or civil, it's almost 1/3 of his market value. So it's a big money involved. So we understand that scenario. There is a lot of money that companies needs to do the provision. The provision is to take the money, save the money, and at the end of the lawsuit, if it's confirmed, then the money goes to the government for the tax or the other part for the labor law. But it's not confirmed that the money comes back to the company. So the way we make the right provisioning, it's money that is right back to the companies, ready for investments. So the Aleph was, so we choose the labor law to start to go into this topic in this kind of this kind of litigation problem, and how we can address these challenges. So we have two pillars here. The first, how we deal with the litigation for itself, how we can defend, how strategies we can elaborate to make good use of our data. And as well, when we talk about in the labor law, of course, the path that we choose, when it's good to make an agreement. So we put several variables to support decisions like that. On the other hand, we have how we can make the operation optimization, which is take the scores of law firms, of lawyers, understand if there is law firm that's good at specific industry, just telecommunications, banks, or if the lawyer is good at some topic, for example, Excel hours. And instead to choose one law firm, we can choose law firms that is good at specific industries, at specific needs. We start our project here in São Paulo. We call that second region. And we have more than 200 of courts, which impacts several documents, unstructured documents to process. Here in Brazil, we have a movement to move to electronic lawsuits for over 3 years, but we have too much information in the physical documents. But it's available in the electronic way, in the same way. In order to collect this data, you use some hacking skills because the information is not easily available. So we have to check the website from the TRTs, search for links. Sometimes we have to generate the IDs to take that link or explore using tools in Python, just like ScryPy, or building our algorithms to take this data collection. But sometimes, even for robots could be very tricky because these websites from the court, there's no API management or something like that. So in order for that, for the courts control the access of information, they use CAPTCHAs. So no problem. Today we can handle that very good. We have here presentations using computer visioning. We use a little bit of computer vision to make a segmentation of images, get 300 of examples, and one simple model of CNN can handle this kind of issue. So we can, of course, collect the data quickly. Putting all together, in order to take our pieces, in order to take our data to do the jurimetric practice, first we need to collect this data that I already told to you. This data, it's in PDF format, RTF, HTML, And after that, we need to convert into pure text file. So after that, we use machine learning techniques, and we use a lot of regular expressions to simple entity extraction. After that, we have a human audit just to keep the high standards of our data extraction. By the end, we delivered all this data organized into web apps that could be accessible by notebooks, tablets, smartphones, or even connected to the data visualization tools. So how we can escalate this process for millions of documents? We choose a public cloud vendor. You run under Azure Cloud, and we keep it at low cost. So our building blocks are here. We have a job management, we have a web app, a set of storage tools, database, one NoSQL, others relational with SQL database, a repository, and a way to do continuous deployment and continuous integration. So here, what we use effectively, since our models are based on Python programming language, just like TensorFlow, scikit-learn, and things related, we need to use Celery as our job management. There are other options, but Celery runs very well. For web application, we choose Rails with Ember.js because we have a small team, and that addresses very, very good. Talking about storage component, you use a Kiwi, blob storage, table, and for data, we have two ways to store the data, as I told to you. NoSQL database, we use Cosmos DB, and MySQL for relational database. Here we have Jenkins for deployment platform and TFS for Git repository. But why we choose those platforms? First, this kind of challenges, we have a little bit of uncertainty. And it's important to keep the team developing and doing new things, have a schema-based database. So with Cosmos DB, we don't have to worry about creating new columns, remove, change data types, and doing configurations a lot. But for the analytics team, they use Tableau, Metabase, data visualization tools that does not talk very well with NoSQL databases. So we create a relational database just for summarizations. Celery, it's a job management tool. It's very, very nice because handle a large amount of jobs. With one virtual machine, we can escalate with several workers and check if there is bottlenecks. There is a visualization panel that helps us to check if everything is running okay. Talking about the storage components at the cloud, we use the blob storage just like S3 from AWS. Here to store our raw documents, the PDF files, then when convert, we store the clean documents and our machine learning models. The Kiwi help us with Celery to keep the concurrency right. So we can start the same tasks 1,000 times at the same time, and the Kiwi keeps one message is with one job. And the table we use for simple configurations. Here we have the Jenkins. So when we start new models, when we start to, for example, new data collections or new validations, since we use the Git repository, when we confirm, when we do all the tests, we push that code for the Jenkins, and the Jenkins is responsible to put that on our environment in the cloud-based. We use Slack for everything. So our monitoring is based on Slack. So Jenkins events, machine learning events, and all cloud events that is important for the team check. We have here a group specific for that. So it's interesting because people related to the product could check if there is new versions or changes in our code. Here, it's our architecture in a very simple way. So all we can do that, everything we do here, it's with these small pieces. So everything is serverless and platform-based except these two virtual machines. And with that, we can deliver to our final customers access to the end users or even connect to their own applications using an endpoint API with API management. So it's very simple. Here there is a mechanical Turk that Rafael will explain further to you. But in small blocks, that's our solution opened entirely for you. Now, Rafael will start to present this part.
Well, talking about the machine learning, deep learning part, the biggest difficulty we found at first was that the texts were written in something that was close to Portuguese, but not quite so. It's an arcane and peculiar language called Brazilian legalese. I can speak it, probably most of you also can't, but the machine would have to. And this is not any standard language on Watson or Google or any platform or interface you can think of. Change the slides. And it has some, so we had to build our own beast. We used some platforms, Keras, TensorFlow.
And OpenCV.
I'm sorry?
OpenCV.
OpenCV, yeah. This one was on Michel's part. And one of the features of this language is that things must be written in the most difficult way. When, for instance, talking about dates, which is something that you usually can easily solve with a regular expression, you have thousands of ways to tell the same date. And the second day of January of 2017. So yeah, the machine will have to figure it out. You also have thousands of patterns. Even the same judge has different standards and templates to write the same thing. So regular expressions were almost excluded from the beginning. These are 4 ways to say the same thing, which is the request was, I don't know, the extra hours or moral harassment, and the conclusion of the judge. So we had to use a very low-tech resource called law students. They're nice to deal with. They're nice. I mean, they don't consume too much energy. But we built an interface where at first they had to do everything manually. They just read the text and said, okay, this is the plaintiff is requesting these 10 things, because no one asks 1 or 2 things. If you're going to sue your company, you ask at least 6. You find at least 6 problems. That's the average, 6 to 8. And the judges decide that these 3 are okay, these 3 are not okay, and they ended up in a deal. And they did it by hand, 1 to 1. And then we built a model on these first examples, and then the results were fed into the database. We used that to create a model, and the predictions were into the database, which were sent to the lawyers, who had an easier time this time, because they had already predictions. They didn't just have to correct what the machine was telling them, and then we made it turn and turn and turn and turn. And as of right now, I guess they are like 10 times faster than they used to be in the first documents. So that's a really a gain for us. And then we had specifically 2 models to classifiers. We both modeled them as text classification problems. First, we divided the text into phrases, and separate it is very hard because they use a lot of abbreviations for instance, doctors, DR point, and every standard tokenizer thinks that the sentence ends there, but that's not the case. So we had to divide the documenting phrases and then say, oh, this phrase is nothing, this phrase is a request, this phrase is a conclusion, and so on and so forth. And then from this classification, we could find what was being requested by the plaintiff. And here we could say, okay, the judge decided that it was granted, it was overruled, and it was a different classification. It was also a text classification problem, because we just fed the text and said, oh, this means yes, and this means, or it means no. Because things should never be so complicated at first, we tried and tested many standard NLP algorithms and many configurations of the same algorithm, so we could see if they worked, and then we went to deep learning when they didn't. And some of them worked. I mean, we use, for instance, many n-grams, I mean, unigrams, bigrams, 3-grams, and different types of stemming, which is getting the root of a word. I mean, you for instance, going, gone means the same thing, go. So you just cut off the last part. And it takes different algorithms to decide which one would work best, and it was quite okay for the second problem, which is decide it was granted or overruled. But it was not enough for all the problems, especially the first one. So we had to go deeper, which means deep learning for you. So traditional NLP for problem 2, deep learning for problem 1. And deep learning, as some of you may know, is in broad strokes composed of 3 layers, just like a Neapolitan ice cream. And the first one means embeddings, which is turning words into numbers so you can feed them to the algorithms. The middle layer are what's traditionally called the deep learning, I mean the sexy part of the thing. And then you have to choose loss function, which will evaluate the model and backpropagate the whole thing. We first, talking about embeddings, there are 2 main approaches to the problem. One is you train the embeddings in a very large corpus, thousands and billions of words, and then transfer them to these models, so you get some information from this big part, or you can train them together with the whole thing, so they are task specific. They're specific to this task you're training on. This is a visualization of the pre-training one, trained on some tens of millions of words. And we got an F-score which was not quite different from the task-specific one. The task-specific, you can see that they tend to, while in this one they tend to cluster on meaning, this one they tend to cluster on the task. So these 3 main clusters probably means, oh, this is the decision, this is a sentence, this is nothing. The words, they're associated with classification. So we went with this one because it generalized a little bit better in unseen words, which require a lot. And in this middle layer, the default choice for deep learning in natural language processing are recurrent neural networks, where you train on a word and then the information is passed to the other one and the other one, and so you have each one is a word, and then you make a phrase, but it's a little bit hard to get information from this first one to get to the last one. And this is pretty common in legalese because judges like to make phrases with tens and, I don't know, 100 lines. So this means not guilty, but the guilty is here and the not is here. So you have to somehow make this dependency work, and a recurrent neural network will have a hard time on that, which is why they invented something called the LSTM, or gated recurrent units. There are many variations to that, where you create a channel that propagates through all the words and many triggers here to use this information. So we ended up with this setup. Actually, we used a 2-layered bidirectional LSTM. Bidirectional means you write from left to right. You run from left to right and then to right to left, because machines can read either way. They don't care like we care. And we also tried different approaches. For instance, try to think of it as each of these columns is a different document. And the colors means the type of phrases you find in the document. So pink means nothing, just headers and footnotes and so on. Green means this is a request. Yellow means this is a sentence. And you see that it's not so unstructured. I mean, you have a structure. You can even model it as a time series. And we tried it, but we failed. And especially because the number of documents is not that big. The number of phrases is really big. The number of words is huge, but the number of documents is pretty small. So even if you use this information to another classifier, the gain was minimal. It was not worth it. But there's information here. We have to tackle it somehow. We tried to create to model the documents as another dimension on the tensor. So you would run here, and then when you condensed all this information in one layer, you still had this layer to model as another time series, and it didn't work. I mean, it was like 5 or 10% less than the simpler model we had. But I'll get there someday. You see. And this is the end solution. I mean, we have, we're still testing most of these features. We had a long way to go to have all the features that we want. But in a nutshell, you can see statistics on judges and lawyers and courts and requests and companies, and try to think the law practice in a more quantitative and analytic fashion. You can try to work with what exactly happened on reality in terms of probabilities instead of the traditional approach from lawyers, which is just to look at what the law says and try to think in principles that the judge mostly ignores. So it's a more reality-based approach, which is at the heart of this concept of jurimetrics, which means using statistics and numbers to legal decisions, to law decisions. These are us. I'm Rafael. He's Michel. And this is email. We're happy to talk with any of you if you have some questions or comments or something else. Thank you.
Thank you.
Is there time for a question?
Yeah, 3 questions, okay?
Hi. Did you have to ask for permission to break those catches?
No, but we did consult quite a few lawyers from our company, and there's no legal restriction per se. It's not forbidden because these are all public data. I mean, it should be available. The law says that they have to be available. So you could even make the case that there shouldn't be a CAPTCHA because this is public information. So we didn't, and I don't know how the legal framework in Brazil is going to evolve from here, but as of nowadays, we are confident that we are not breaking the law in any way.
Hi, could you talk a little bit about the results that you had? Because you talk a lot about the model, but the problem of litigation in Brazil is huge for the companies. So do you have any example of this model that has been deployed in a certain company and they made decisions in terms of making reserves or maybe doing some agreements with the plaintiffs, and what kind of cost savings did they have?
There are many cost savings. We still don't have these predictive models that will allow you to say, "Oh, go for a deal on this one." We are working on that. It's being planned right now. But we can see already some pretty big gains because most legal departments have paralegals or even lawyers working on updating Excel sheets mostly, to be honest. With all the information on each of the tens or hundreds of thousands of cases some companies have in Brazil, especially in the labor sector. And it's pretty hard to keep up with the cases of a single company, let alone a whole sector or more things. So we already have some projects just to organize the information on legal departments, and then we'll scale that to increased visibility of what happens in courts, and even predictive models and so on.
Two questions. The first is how many documents were like crawled from the websites? I saw 5,000 processes in the last slide. So how big was the data set you guys crawled to build the model? And the second is you split the models into phrases to be labeled, being requested, etc. So how many law students were needed to label this, and how many phrases? So the phrases in terms of volume, how many phrases and documents you crawled? And also if you could say, like, I guess the government, the servers were not like expecting the traffic you guys drove to run. So did you got any like...
Well, we have at least 80 millions of documents. Of course, we did not download 80 millions in 1 hour. We have been working on that for more than a year. So we control our collectors to not make the DOS. We have some intervals, and we schedule the collectors to run more often during the off hours. So during the commercial hours, we do not use these data collectors, just to preserve the platform and not to exploit it to download every time, every second.
Regarding the second question, it was not exactly an army of lawyers. I mean, I think at most we had 2 working simultaneously. But it's been a long time, I mean, more than 6 months. So, yeah, I mean, and as I explained, we have they're accelerating, so they're way more productive than they used to be. The first approaches were even discarded because the data was not tagged in a way that was nice and useful for the models we were creating. So there's a learning curve on that too.
Okay, thanks. Thank you, Rafael. Thank you, Michel. Beautiful work.